You think our cosmic home, the Milky Way, is just some average middle-of-the-road galaxy? That's what almost everyone believes, but that belief is completely wrong. The shocking truth is that our galaxy is a genuine colossal structure, one of the top 5% of the largest in the entire observable universe. It's so enormous, light takes 100,000 years just to cross it. A true giant towering over the countless tiny dwarf galaxies that make up the real average. We are anything but ordinary. Before we expose the true cosmic monsters that still dwarf a galaxy as huge as ours, hit that like and subscribe button, because what we're about to uncover will completely change how you see our place in the universe. Prepare yourselves, we begin. When you gaze up at the night sky and see that faint glowing band stretching across the darkness, you're actually staring edge-on through the spinning disk of our home galaxy. But here's the shocking part. You're not looking at the heart of the action, because we're stuck way out in what astronomers call the galactic suburbs, roughly 26,000 light-years from the Milky Way's blazing center. To put that distance into perspective, if light itself, traveling at an absolutely insane 186,000 miles per second, left the galactic core and headed straight toward us, it would take 26,000 years to arrive, meaning the light we see from that direction today actually started its journey long before humans built the pyramids or invented writing. We're perched on the inner edge of something called the Orion Arm, which isn't even one of the major spiral arms, but more like a spur or bridge, connecting two larger structures, the Perseus Arm and the Sagittarius Arm. Think of it this way. If the Milky Way were a bustling metropolis, we'd be living in a quiet neighborhood on the outskirts, far from the densely packed downtown core where stars crowd together so tightly that if we somehow lived near the galactic center, our night sky would blaze with 1,000,000 stars, as bright as Sirius, the brightest star visible from Earth, and the sky would stay so illuminated it would barely feel different from daytime. Instead, our solar system sits roughly halfway out toward the edge of the visible disk, depending on how you measure it. Because the galaxy doesn't have a sharp boundary, it fades gradually as you move outward. The main disk, where most of the stars reside, extends about 50,000 light-years in all directions from the center, making the total diameter around 100,000 light-years. So at our position, 26,000 light-years out, we're neither in the thick of things nor completely isolated. But distance isn't the only thing that makes our location unusual. We're also sitting almost perfectly on the galactic plane, just 95 light-years above the central disk, which means we have a side-on view slicing right through the densest concentration of stars, gas, and dust. This angle is both a blessing and a curse. It gives us that iconic Milky Way band across the sky, but it also makes it incredibly difficult for astronomers to map the galaxy's true structure, because we're looking through layers and layers of obscuring material that blocks our view. Early astronomers had no idea we were off-center at all. They assumed the sun sat near the middle of everything, because from our vantage point, stars seemed to spread out evenly in all directions. It wasn't until the early 20th century that Harlow Shapley, studying globular clusters, those ancient spherical swarms of stars orbiting the galaxy, noticed something strange. Almost all the clusters he observed were concentrated in one part of the sky, toward the constellation Sagittarius. He realized these clusters weren't orbiting us, but were instead circling something else entirely, something massive and distant. And that revelation shattered the long-held belief that we occupied a central position. Shapley calculated the distance to the galactic center, but got it wrong by a factor of 2, because he didn't account for interstellar dust dimming the light from distant objects, making them appear farther away than they really were. Yet his fundamental insight was correct. We were out in the sticks, not at the hub. Modern measurements using stars orbiting the supermassive black hole at the galactic center, known as Sagittarius A star, have refined our distance estimate to about 27,000 light-years. give or take a few hundred light years depending on the method used. Some studies analyzing stellar orbits have calculated values as precise as 27.14 thousand light years, while others suggest slightly smaller figures around 25.64 thousand light years, but all agree we're nowhere near the middle. Our position in the Orion Arm also places us in what scientists call the galactic habitable zone, a region far enough from the chaotic core to avoid deadly radiation bursts and supernova blasts, but close enough to benefit from the heavier elements forged in earlier generations of stars. If we lived too close to the center, the intense radiation from the supermassive black hole and the frequent explosions of massive stars would sterilize planets and make life nearly impossible. But too far out, and there wouldn't be enough heavy elements like carbon, oxygen, and iron to build rocky planets or complex molecules. Our suburban location strikes a balance, quiet enough to be safe, rich enough in resources to build worlds. Adding to the intrigue, some models suggest the sun didn't even form where it is now, but was actually born much closer to the galactic center, around 16,000 light-years in, and then migrated outward over billions of years to its current position. This radial migration happens because gravitational interactions with spiral arms and other galactic structures can nudge stars inward or outward over time, shuffling the stellar population like a slow cosmic dance. If that's true, then our solar system has spent billions of years wandering through different neighborhoods of the galaxy, experiencing varying levels of star density, radiation, and elemental abundance along the way. The sun's journey doesn't stop here either. Right now, we're orbiting the galactic center at a blistering speed of around 140 miles per second, though you'd never feel it because everything around us is moving together in the same direction. At that pace, it takes roughly 225 to 250 million years to complete one full orbit, a time span astronomers call a galactic year, meaning the last time the solar system was in this exact position. Dinosaurs hadn't even appeared yet. In fact, since Earth formed about 4.5 billion years ago, we've looped around the galaxy only about 20 times, and each orbit carries us through different regions, sometimes plunging through dense spiral arms, where star formation is active, and sometimes cruising through quieter spaces between the arms. These passages through spiral arms aren't without consequences. Some scientists speculate that increased exposure to cosmic rays and nearby supernovae during arm crossings could trigger mass extinctions or climate shifts on Earth, though the evidence remains debatable. What's undeniable is that our location profoundly shapes what we see and how we understand the universe. Being embedded in the disk means we can't simply step back and admire the Milky Way's grand spiral structure the way we can with distant galaxies like Andromeda. Instead, astronomers have painstakingly mapped our galaxy piece by piece, using radio waves to peer through dust, measuring the motion and distance of millions of stars, and even sending space telescopes beyond Earth's atmosphere to get clearer views. Missions like Gaia have revolutionized our understanding by precisely tracking the positions and velocities of over 1 billion stars, revealing details about the Milky Way's shape, rotation, and history that were impossible to see before. These observations confirmed that we sit in a relatively calm patch of the galaxy, surrounded by a mix of young and old stars, with the nearest major spiral arm, the Perseus arm, about 6,500 light-years farther out from us, and the Sagittarius arm, a similar distance inward. Between these arms, star formation is less intense, and the space is filled with diffuse gas, dust, and older stars slowly orbiting the galactic center. But even within our local arm, there are fascinating structures like the Radcliffe Wave, a vast undulating band of gas and star-forming regions that ripples through our neighborhood, or the local bubble, a roughly 300 light-year wide cavity carved out by ancient supernova explosions that cleared away much of the gas and dust in our immediate surroundings. The sun currently sits near the inner edge of this bubble, in a small region called the local fluff, which sounds whimsical, but is actually a technical term for a patch of slightly denser gas within the bubble. This local environment influences everything from the flow of interstellar particles into the solar system to the way we detect distant cosmic phenomena. Our suburban address also means we're relatively safe from the dangers lurking near the galactic core, where the supermassive black hole, weighing in at about 4 million times the mass of the Sun, devours anything that strays too close and occasionally belches out powerful jets of radiation. Closer to the center, stars orbit so fast and pass so near to each other that planetary systems would be gravitationally disrupted, and any life that managed to form would be bombarded by radiation from nearby stellar explosions and the black hole's accretion disk. Out here, the pace is slower, the stars are more spread out, and the environment is stable enough for planets to orbit peacefully for billions of years, giving life a fighting chance to emerge and evolve. Yet, despite our relative safety, we're not completely isolated. Our galactic neighborhood is still a dynamic place, where new stars are born. In nearby nebulae, old stars explode as supernovae, and clouds of gas and dust drift past us on their own orbits around the galaxy. The very fact that we're located in the Orion Arm, a minor structure compared to the major Perseus and Sagittarius arms, raises interesting questions about how spiral arms form and persist. Are they permanent features carved into the galaxy's structure? Or are they transient waves of density that sweep through the disk, compressing gas and triggering bursts of star formation before dissipating? Current evidence suggests they're a bit of both, with some arms being long-lived and others more ephemeral, and our position in a smaller arm hints that we might be riding through one of these temporary density waves. Measuring our exact position has been one of the great challenges of astronomy, precisely because we're inside the very structure we're trying to map. Imagine trying to draw a detailed map of a forest while standing in the middle of it, with trees blocking your view in every direction, and you'll get a sense of the difficulty. For decades, astronomers could only estimate the distance to the galactic center by observing the distribution of globular clusters, the motions of nearby stars, and the brightness of certain variable stars called Cepheids. But modern techniques, using radio observations of masers, naturally occurring cosmic lasers, and the orbits of stars near Sagittarius A star, have dramatically improved our accuracy. These stars, orbiting the black hole at incredible speeds, act like cosmic GPS markers, allowing scientists to triangulate the distance with unprecedented precision. Even so, uncertainties remain, because the Milky Way isn't a perfect symmetric structure. It's warped, twisted, and lopsided in ways we're still figuring out, and those irregularities affect how we measure distances and velocity. Our off-center location also means we're constantly being reminded that we're not the center of anything, not the solar system, not the galaxy, not the universe, and each discovery that pushes us farther from the middle is a humbling reminder of our place in the cosmos. The fact that we can even determine our position within the galaxy is a testament to human ingenuity and our relentless curiosity about the universe, because from our limited vantage point, wedged into the galactic disk, we've managed to piece together a map of a structure so vast that light takes 100,000 years to cross it. And yet, despite being stuck in the suburbs, our location offers a unique perspective. We can study the processes happening in spiral arms, observe the flow of gas and stars through the disk, and watch the interplay between the galaxy's magnetic fields and cosmic rays, all while being close enough to the action to gather meaningful data, but far enough to avoid being fried by radiation or swallowed by the black hole. So while we might not live in the penthouse suite at the galaxy's core, our quiet neighborhood 26,000 light-years out has proven to be the perfect spot for a curious species to look up ask questions, and slowly unravel the mysteries of the vast cosmic city we call home. For centuries, astronomers believed they had a decent grasp of the Milky Way's size and structure. A grand spiral disk packed with stars, gas, and dust, stretching roughly 100,000 light-years across. But recent discoveries have completely upended that comfortable picture, revealing a galaxy far stranger, larger, and more dynamic than anyone imagined. The breakthrough came from missions like Gaia, a European Space Agency telescope, launched specifically to map our galaxy with unprecedented precision. By measuring the positions, distances, and motions of over 1 billion stars. And what Gaia found was nothing short of revolutionary. Instead of the neat, orderly spiral we expected, the data revealed a galaxy that's warped, lopsided, and filled with hidden structures that were completely invisible until now, including vast streams of stars torn from smaller galaxies that the Milky Way devoured millions of years ago. But the surprises didn't stop with stars. Scientists also discovered that the Milky Way is enveloped in multiple layers of gas, some cold and dark, others blazing hot at millions of degrees, creating a complex, multi-phase halo that extends far beyond the visible edge of the galaxy. This gaseous cocoon, known as the circumgalactic medium, isn't just sitting there passively. It's actively recycling material, with dying stars ejecting gas outward into the halo, while fresh material falls back down onto the galactic disk to fuel the next generation of star formation, creating a cosmic cycle of birth, death, and rebirth that's been going on for billions of years. What's even more mind-blowing is that this halo of hot gas extends an astonishing 700,000 light-years from the galactic center, which means the Milky Way's true reach is nearly 7 times wider than the visible disk we typically think of when we picture our galaxy. This superhot gas, heated to around 10 million degrees Kelvin, glows faintly in X-rays, and researchers using a tiny spacecraft called HaloSat, roughly the size of a toaster, discovered that this halo isn't spherical, but disk-like, with brighter X-ray emissions, concentrated above regions where star formation is most vigorous. The intensity of these emissions gave scientists a crucial clue. The hot gas is directly linked to stellar activity, particularly supernovae, those catastrophic explosions that mark the deaths of massive stars and pump enormous amounts of energy and heavy elements into the surrounding space. Every time a massive star explodes somewhere in the Milky Way's disk, it blasts its outer layers into space at thousands of miles per second, heating the surrounding gas to extreme temperatures and enriching it with alpha elements like sulfur, magnesium, and neon elements forged in the star's core through nuclear fusion. This fiery, turbulent gas then swirls violently around the disk, either escaping into the broader circumgalactic medium or cooling down and falling back onto the galaxy to seed new stars. And this continuous feedback loop is what keeps the Milky Way alive and evolving. But the hot gas isn't the only hidden layer. There's also a vast network of cold, dark gas that doesn't emit light in the visible spectrum and remained almost completely invisible until astronomers began mapping it using radio telescopes. This mysterious dark gas weaves through star-forming regions in intricate patterns, arcs, ridges, and web-like filaments. And it's precisely this material that collapses under gravity to form new stars, making it absolutely critical to understanding how galaxies grow. In regions like Cygnus X, one of the Milky Way's most active star factories, radio observations revealed dense clumps and streams of this dark gas threading through the clouds, showing where future stars will eventually ignite. Scientists also discovered that cosmic dust, those tiny grains of silicates and carbon compounds floating between the stars, is not evenly distributed across the galaxy, but instead forms a thin, wavy layer that doesn't align perfectly with the galactic plane. This reddening plane, as astronomers call it, shifts up and down in a wave-like pattern as you look around the galaxy, with the most dust concentrated around a galactic longitude of 41 degrees and the least around 221 degrees. The Sun itself sits roughly 50 light-years above this dusty layer, which means our view outward is relatively clear compared to other parts of the galaxy, where thick dust lanes completely obscure entire regions from view. This uneven distribution of dust has major implications for astronomy because dust absorbs and scatters visible light, making distant stars appear dimmer and redder than they actually are. A phenomenon called interstellar extinction. For decades, this dust frustrated astronomers trying to map the galaxy's structure because whole sections of the Milky Way were hidden behind impenetrable veils of gas and dust, particularly in the direction of the galactic center, where the dust is thickest. But the advent of infrared and radio telescopes changed everything. Infrared light penetrates dust much better than visible light, allowing astronomers to peer through the obscuring layers and see what's hidden beneath. The James Webb Space Telescope, with its powerful infrared instruments, recently captured images of star-forming regions, where scientists saw stars that had been completely invisible. Until now, their light buried beneath layers of gas and dust, so thick that no optical telescope could ever detect them. Webb's observations also revealed narrow tunnels carved through dense clouds by stellar winds and outflows, creating escape routes where light can slip through and giving astronomers an unprecedented glimpse into how massive star clusters take shape. These discoveries are rewriting our understanding of star formation, showing that the process is far more complex and chaotic than the neat, orderly collapse of gas clouds depicted in textbooks. Meanwhile, astronomers using the CSIRO Parkes radio telescope in Australia made another stunning find. They discovered hundreds of galaxies hidden directly behind the Milky Way in a region ominously called the Zone of Avoidance. This zone, located in the direction of the galactic center, is so choked with dust and gas that it completely blocks our view of the universe beyond, creating a blind spot in our maps of the cosmos. By using radio waves to peer through the Milky Way's thick layers, researchers found entire galaxies that had been lurking in the shadows, including some that may help explain a mysterious gravitational anomaly called the Great Attractor, a massive concentration of mass pulling our local group of galaxies toward it at hundreds of miles per second. The discovery that so much of the galaxy's structure and contents had been hidden from view until very recently is humbling. It means that for most of human history, we've been working with incomplete information, building models based on what we could see while huge chunks of the picture remained invisible. The Milky Way's surprises aren't limited to what's hidden. There's also the question of what's missing, specifically the missing baryonic matter that cosmologists have been hunting for decades. Based on measurements of the early universe and models of the Big Bang, scientists calculated how much ordinary matter, protons, neutrons, electrons, the stuff that makes up stars, planets, and people, should exist in the universe today. But when they added up all the matter they could actually observe in galaxies, stars, and gas clouds, they came up short by about 1/3. Where did all that missing matter go? Some researchers suspected it might be hiding in the diffuse, super-hot halos surrounding galaxies like the Milky Way. But proving that has been incredibly difficult, because this gas is so spread out and faint that it barely emits any detectable radiation. Halo's observations showed that the Milky Way's circumgalactic medium is clumpier and more structured than expected, with dense regions concentrated near star-forming areas. But the spacecraft couldn't determine whether there's a truly massive extended halo, stretching far beyond the bright inner regions. If such a halo exists and is dim in X-rays, it could potentially house enough material to account for some of the universe's missing baryons. But the bright emission from the inner halo makes it difficult to detect the faint outer layers. The search continues, with astronomers now combining data from multiple X-ray observatories to piece together a complete picture of the Milky Way's gaseous envelope and calculate whether it's massive enough to solve the missing matter puzzle. Another revelation that shocked the astronomical community is just how much the Milky Way has grown by cannibalizing smaller galaxies over billions of years. Gaia's data revealed streams of stars with unusual orbits and chemical compositions, telltale signs that they didn't form in the Milky Way, but were once part of dwarf galaxies that ventured too close and got torn apart by tidal forces. These stellar streams now wrap around the Milky Way like ghostly ribbons, preserving evidence of ancient collisions and mergers. And some of the largest streams contain the remnants of galaxies that were devoured as recently as 2 billion years ago, while others record events stretching back nearly to the Milky Way's formation. Each discovery adds another layer of complexity to the story. What we once thought of as a simple spiral galaxy is actually a dynamic, evolving system that's constantly accreting new material, recycling old stars, and interacting with its surroundings in ways we're only beginning to understand. The realization that the Milky Way is surrounded by invisible layers of gas, veiled by shifting plains of dust, and stretched far beyond its visible boundaries, forces us to rethink everything we thought we knew about our home galaxy's true scale and nature. And it raises an unsettling question. If we've missed so much about the galaxy we live in, what else are we still not seeing? If you thought the Milky Way was a neatly arranged spiral, sitting perfectly flat in space like a cosmic dinner plate, prepare to have that image shattered. Our galaxy is twisted, warped, and wildly asymmetric in ways that astronomers never anticipated until they started mapping it with extraordinary precision. The galactic disk, rather than lying in a single flat plane, curves and ripples along an S-shaped pattern that makes the entire structure look like it's been grabbed at opposite ends and twisted in different directions, with some edges flaring upward, while others dip downward in a cosmic roller coaster that defies the neat textbook illustrations we grew up with. This warping was first hinted at decades ago, when radio astronomers noticed that clouds of neutral hydrogen gas, the raw material for star formation, didn't all sit at the same height above the galactic plane, but instead formed a twisted disk that spiraled up and down as you traced it around the galaxy. At first, scientists thought this might just be an artifact of measurement errors, or perhaps limited to the gas alone. But when the Gaia Space Telescope started precisely measuring the positions of millions of stars, it confirmed the shocking truth. The stars themselves follow this warped structure, meaning the entire disk is bent out of shape. The warp becomes most pronounced at the galaxy's outer edges, more than 40,000 light-years from the center, where the disk's northern half tilts upward by several thousand light-years, while the southern half dips downward, creating a lopsided, twisted appearance that looks nothing like the symmetrical spirals we see in images of distant galaxies like Andromeda. What could possibly cause such dramatic distortion in a structure as massive as the Milky Way, a galaxy containing hundreds of billions of stars and weighing in at roughly 1 trillion times the mass of the Sun? The answer involves a combination of gravitational bullying from nearby galaxies and the mysterious influence of dark matter, that invisible substance that makes up the majority of the galaxy's mass, but refuses to interact with light in any way we can directly detect. The Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way like cosmic satellites, exert significant gravitational pull as they swing around our galaxy, and their combined mass, though small compared to the Milky Way itself, is enough to tug on the outer edges of the disk and induce oscillations that propagate through the structure like ripples on a pond. Computer simulations show that when a massive object passes by or through a galactic disk, it can trigger waves of density that cause the disk to wobble and warp, and the effect is particularly strong at the edges where the material is less tightly bound by the galaxy's gravity. But the Magellanic Clouds aren't the only culprits. The Milky Way is also being influenced by the gravity of Andromeda, the nearest large spiral galaxy, located about 2.5 million light-years away. And even that enormous distance isn't enough to prevent gravitational interactions between these two massive structures, especially since they're slowly falling toward each other and will eventually collide in roughly 4 billion years. The dark matter halo that surrounds the Milky Way, extending far beyond the visible stars and gas, plays a crucial role in shaping the galaxy's structure, because this halo is neither perfectly spherical nor evenly distributed, and its irregular shape creates gravitational torques that twist and warp the disk in complex ways. Recent gamma-ray observations have provided tantalizing hints about this dark matter halo. NASA's Fermi Gamma Ray Space Telescope detected a mysterious glow of gamma rays with energies around 20 gigaelectronvolts, extending in a halo-like structure toward the Milky Way's center. And the shape of this emission closely matches what theoretical models predict for a dark matter halo. The gamma rays, which carry an absolutely enormous amount of energy, 20 billion electron volts per photon, could be produced by dark matter particles annihilating each other when they collide, converting their mass into pure energy in the form of high-energy radiation. This signal, if confirmed to be dark matter, would represent the first direct detection of this elusive substance after nearly a century of searching, though scientists caution that other explanations involving cosmic rays and interstellar gas interactions need to be ruled out before claiming a definitive discovery. But the warp isn't the only wild feature astronomers have uncovered. The Milky Way's disk is also broken in places, with a recent NASA study identifying a mysterious 230 light-year break in the galactic structure that shows irregular bending, sharp edges, and uneven density patterns that suggests something powerful recently disturbed the galaxy. This break, located in one of the spiral arms, couldn't have formed gradually through normal galactic processes, but must have resulted from a violent external force, possibly a close encounter with a dwarf galaxy, or an unusually energetic burst of star formation that blasted material out of the disk. The sharp edge and irregular shape indicate that this disruption is relatively recent in cosmic terms, because if it had happened billions of years ago, the structure would have smoothed out and dispersed by now. But instead, the galaxy is still reeling from whatever event caused this damage. Adding to the chaos, astronomers have discovered massive bubbles of superheated gas and high-energy particles ballooning out from the galactic center, extending thousands of light-years above and below the disk in structures called the Fermi bubbles, named after the telescope that first spotted them in 2010. These enormous structures, glowing with gamma rays and X-rays, were likely created by a powerful outburst from the supermassive black hole at the galaxy's core, possibly triggered by a massive influx of gas that the black hole devoured in a feeding frenzy sometime in the past few million years. The energy released by this event was so tremendous that it carved out gigantic cavities in the surrounding gas and accelerated particles to nearly the speed of light, creating the glowing bubbles we see today. But even more bizarre structures have been found lurking within these bubbles. Researchers using radio telescopes recently discovered magnetized filaments stretching over 16,000 light-years in height, reaching temperatures of 3.5 million Kelvin, and forming thin, organized structures that connect star-forming regions at the edge of the galactic bar to the outer halo. These filaments aren't coming from the black hole itself, but appear to be linked to vigorous star formation at the bar's edge, where massive stars are blowing powerful winds and exploding as supernovae, pumping energy and magnetic fields into the surrounding space. The discovery shows that magnetic fields play a far more important role in shaping the galaxy's structure than previously thought, influencing the motion of gas and dust, and even affecting where new stars can form by channeling material along magnetic field lines. The Milky Way's central bar, that elongated structure of stars cutting through the galactic core, is itself a source of dynamism and chaos. Because unlike the disk, which rotates at a relatively steady pace, the bar spins at a different rate and acts like a giant gravitational stirring rod, funneling gas from the outer disk toward the center, where it can fuel star formation or feed the supermassive black hole. This bar wasn't always there. Simulations suggest it formed several billion years ago, when the disk became gravitationally unstable, and stars began organizing themselves into this elongated pattern. And the bar's presence has fundamentally altered the galaxy's evolution. The Milky Way's wild, twisted structure is also marked by ripples and waves that propagate through the disk like sound waves through water, with some of these oscillations caused by ancient collisions with smaller galaxies that the Milky Way absorbed billions of years ago. One such collision, now called the Virgo radial merger, appears to have happened roughly 2.7 billion years ago, when a dwarf galaxy plunged through the Milky Way's disk, creating shock waves that are still reverberating today. The evidence for this event comes from unusual patterns in stellar motions, groups of stars moving in coordinated ways that can only be explained by a massive disruption sometime in the past, and these findings push back the timeline for the Milky Way's last major collision by roughly 5 billion years. Compared to previous estimates that placed it around 8 billion years ago, the collision likely brought numerous smaller dwarf galaxies along with it, many of which were shredded by tidal forces, and now exist only as streams of stars orbiting the galaxy, while others may have survived intact as some of the globular clusters we observe today. Beyond the warped disk and mysterious breaks, astronomers have also found enormous ring-like structures rippling above and below the galactic plane, including the triangulum Andromeda ring, a filament of stars stretching at least 50 kiloparsecs, roughly 160,000 light-years, in diameter, and possibly representing part of the Milky Way's outer disk that's been severely warped and stretched by gravitational interactions. The Monoceros ring, another massive structure encircling the galaxy, was initially thought to be the remnant of a cannibalized dwarf galaxy, but more recent analysis suggests it might simply be an overdensity produced by the flared and warped thick disk, a sign of how chaotic and asymmetric the Milky Way's structure really is. All these features, the S-shaped warp, the broken arm, the massive bubbles, the magnetized filament, the rippling rings, paint a picture of a galaxy that's far more dynamic and violent than the serene spiral we imagine when we look up at the night sky and they reveal that galactic evolution isn't a smooth, orderly process, but a messy, chaotic saga of collisions, explosions, and gravitational tug-of-war that continues to shape the Milky Way even today. The realization that our home galaxy is twisted, broken, and riddled with scars from ancient battles forces us to confront an uncomfortable truth. The Milky Way isn't some perfect, pristine structure, but a work in progress, constantly being reshaped by forces both internal and external. And what we see today is just a snapshot of a galaxy in flux, caught in the middle of a cosmic transformation that's been unfolding for billions of years and will continue for billions more. For decades, astronomers assumed the Milky Way was a pretty standard spiral galaxy. Nothing special, just one of countless similar structures scattered throughout the universe. But a series of groundbreaking studies over the past few years has completely overturned that assumption, revealing that our home galaxy is actually a cosmic oddball in ways that raise profound questions about galactic evolution and our place in the universe. When researchers compared the Milky Way to hundreds of other spiral galaxies with similar rotation speeds and masses, they discovered something startling. For a galaxy spinning as fast as ours, the Milky Way has a surprisingly small disk radius and dramatically lower stellar mass than what you'd expect, making it roughly twice as compact as the average spiral galaxy. In fact, only 7% of nearby spiral galaxies share properties similar to the Milky Way, which means if you randomly picked a spiral galaxy from the universe, there's a 93% chance it would look quite different from our home. Compare that to Andromeda, our nearest large galactic neighbor located about 2.5 million light-years away, which has completely average properties for a spiral galaxy of its size. Andromeda fits neatly into the expected patterns, while the Milky Way stands out as an anomaly. But the weirdness doesn't stop at size and mass. The Milky Way's satellite galaxies, those smaller dwarf galaxies orbiting around us like cosmic moons, also behave in highly unusual ways compared to satellite systems around other galaxies. The SAGA survey, which stands for Satellites Around Galactic Analogs, spent years studying galaxies similar in mass to the Milky Way to understand what a typical satellite system should look like. And what they found shocked the astronomical community. Most Milky Way-like galaxies have numerous satellite galaxies actively forming stars, with about 1/3 of these systems containing at least one satellite as massive as the Large Magellanic Cloud. And these galaxies typically host more satellites overall than the Milky Way does. Our galaxy, however, has a strangely lopsided satellite system. We have two massive satellites, the Large and Small Magellanic Clouds, which are actively forming stars, and only recently fell into the Milky Way's gravitational embrace. But the vast majority of our other satellites are small, faint, and have had their star formation completely shut down billions of years ago. This pattern is backwards compared to most galaxies. Typically, you'd expect smaller satellites to be quenched more easily, because they have less mass and gravity to hold onto their gas, while larger satellites continue forming stars. But around the Milky Way, we see mostly dead small satellites and only a couple of large active ones. Scientists are puzzling over what could have caused this unusual configuration. One theory suggests that the Milky Way acquired most of its satellites much earlier in its history than similar galaxies did, giving it billions of extra years to strip away their gas and shut down star formation before the recent arrival of the Magellanic Clouds. When satellites fall into a larger galaxy's gravitational field, they experience tidal forces that can rip gas away from them, and close passes to the galactic core can heat or strip this gas entirely, rendering the satellite unable to form new stars, a process astronomers call quenching. Leo 1, a faint dwarf galaxy orbiting the Milky Way near the bright star Regulus, experienced exactly this fate. About 1 billion years ago, it made a close approach to the Milky Way's center, had most of its star-forming gas torn away, and has been essentially dead ever since. The stripped gas doesn't just disappear. It becomes part of the Milky Way's vast circumgalactic halo, that enormous envelope of hot gas surrounding the galaxy, which means the Milky Way has been building itself up by cannibalizing its satellites over billions of years. But here's where things get even stranger. The Milky Way's entire environment is unusual, not just the galaxy itself, because we happen to reside within something called a cosmological wall, specifically the local which is a flattened arrangement of galaxies, surrounded by vast empty voids on either side. These voids act like cosmic pressure, squashing galaxies together into a pancake-like distribution. And this unique environment influences how the Milky Way and its neighbors rotate and move through space in a more organized way than if we were located in a random part of the universe. If you could somehow see the sky from a vantage point far outside our local region, you'd notice that the nearest dozen or so large galaxies all lie roughly on a ring embedded in this local sheet, an arrangement that's already somewhat special on its own. But researchers recently discovered something that makes the Milky Way's situation even more remarkable. When they examined other cosmological walls throughout the universe, they found that walls like the local sheet very rarely contain a galaxy as massive as the Milky Way. In other words, the Milky Way is too big for its wall. Most galaxies of our mass live in much denser environments, with many more neighboring galaxies, while walls typically host only smaller, less massive galaxies. To find another cosmological wall containing a Milky Way-sized galaxy, you'd have to travel roughly 500 million light-years away, passing thousands upon thousands of other galaxies along the way. That's about 200 times farther than the distance to Andromeda, making the Milky Way's cosmic neighborhood genuinely rare. Some astronomers caution that you have to be careful about declaring things special, Because if you set ridiculously restrictive conditions like demanding that a galaxy must contain the exact research paper describing this phenomenon, then obviously you'd be unique. But the too big for its wall property appears to be physically meaningful and observationally significant enough to legitimately call out as unusual. The Milky Way's peculiarities extend to its halo as well. The ancient stars that populate the spherical halo surrounding the galactic disk are surprisingly poor in heavy elements compared to halo stars in other spiral galaxies, suggesting our galaxy had a different chemical enrichment history. Heavy elements, everything heavier than hydrogen and helium, are forged in the cores of massive stars and scattered into space when those stars explode as supernovae. So a galaxy's metallicity, the abundance of these heavy elements, tells you about its star formation history and how many generations of stars have lived and died enriching the gas. The Milky Way's metal-poor halo indicates it underwent very few major mergers with other large galaxies over the past 10 to 11 billion years. Because mergers typically trigger intense bursts of star formation that rapidly enrich the gas with heavy elements, most spiral galaxies have experienced multiple significant mergers throughout their lives, each one adding mass, triggering star formation, and fundamentally reshaping the galaxy's structure. But the Milky Way appears to have had a remarkably calm existence by galactic standards, growing mostly through the gradual accretion of small dwarf galaxies, rather than violent collisions with equals. This quiet history explains why the Milky Way has a smaller disk and lower stellar mass than expected. Mergers tend to funnel gas toward the galactic center, triggering massive bursts of star formation that rapidly build up the galaxy's mass and extend its disk. But without those dramatic events, the Milky Way grew more slowly and steadily. Yet despite this apparently peaceful path, recent discoveries show the Milky Way has been anything but calm. Astronomers using data from the Gaia Space Telescope discovered enormous ripples, or waves, spreading across the galactic disk, vertical distortions that affect stars located between 30,000 and 65,000 light-years from the galactic center, covering a huge fraction of the entire galaxy. This structure, dubbed the Great Wave, looks like a gigantic ripple, moving through the disk when viewed edge-on, with some regions tilted upward and others dipped downward in a sinusoidal pattern that extends for tens of thousands of light-years. What's truly bizarre is that stars caught in the crest of this wave aren't just moving up and down, they're also being pushed systematically outward from the galactic center at speeds of 10 to 15 kilometers per second, which is unusually high for a typical galaxy and suggests something powerful disturbed the Milky Way structure relatively recently in cosmic terms. The most likely explanation is that this wave was triggered by a dwarf galaxy that plunged through the Milky Way's disk sometime in the past few billion years, creating shock waves that are still propagating outward like ripples on a pond after a stone is thrown in. And this finding reveals that even though the Milky Way avoided major mergers, it still experienced violent interactions that left lasting scars. The combination of all these unusual properties, the undersized disk, the metal-poor halo, the strange satellite system, the too big for its wall environment, and the massive propagating waves, paints a picture of a galaxy that doesn't fit neatly into any category, and it raises uncomfortable questions about how representative the Milky Way is when we use it as a template for understanding galaxy formation and evolution across the universe. Are the physical processes we observe happening here typical of what happens in other galaxies? Or is our perspective fundamentally skewed by living in an outlier? When we study star formation, galactic structure, dark matter halos, and supermassive black holes, using the Milky Way as our primary laboratory, are we actually learning universal truths about how galaxies work? Or are we just learning about the quirks of one unusual example? Some researchers argue that living in a slightly atypical galaxy might actually be good for life. The Milky Way's quiet merger history meant fewer catastrophic events that could have disrupted planetary systems or sterilized regions of the galaxy with radiation, and our position within a cosmological wall rather than a dense galactic cluster means we're far from the intense radiation and tidal forces found in those crowded environments. Earth itself is unusual. We orbit a single stable star in the habitable zone. We have an unusually large moon. Our solar system has a neat division between rocky inner planets and gas giants farther out. And now it turns out we live in an unusual galaxy in an unusual cosmic environment. Is this a coincidence? Or is there something about unusual environments that makes them more conducive to the emergence of complex life and technological civilizations? The Milky Way's peculiarities also complicate efforts to understand dark matter, because most of our constraints on dark matter's properties come from observing how it behaves in our galaxy, measuring rotation curves, tracking stellar streams from disrupted satellites, and mapping the density distribution of the dark matter halo. But if the Milky Way is atypical, then the dark matter properties we measure here might not perfectly represent what's happening in more typical galaxies. The invisible dark matter halo surrounding the Milky Way, which outweighs all the visible stars and gas by at least 10 to 1, provides the gravitational scaffolding that holds the galaxy together and determines its rotation speed. But the exact shape, density profile, and substructure of this halo depend on the galaxy's formation history, and an unusual history could produce an unusual halo. Recent observations suggesting gamma-ray signatures, potentially from dark matter annihilation in the Milky Way's halo, are exciting, but they need to be interpreted carefully, given that our galaxy doesn't represent a typical environment. The bottom line is that the Milky Way, far from being an average run-of-the-mill spiral galaxy, is turning out to be a cosmic weirdo in multiple independent ways, and recognizing this forces astronomers to rethink how much they can generalize from observations of our home to understanding the broader universe of galaxies. The Milky Way didn't reach its current size and structure by peacefully accumulating gas and dust from the primordial universe. Instead, like a cosmic predator, it grew by violently devouring smaller galaxies that wandered too close, tearing them apart with relentless tidal forces and scattering their stars across the galactic halo in ghostly streams that still wrap around our galaxy today. This process, which astronomers call galactic cannibalism, is believed to be the typical mode of growth for massive galaxies throughout the universe. And the evidence for the Milky Way's violent past is written all over the sky if you know where to look. The first major clue came in 1994 when astronomers discovered the Sagittarius dwarf elliptical galaxy, a small galaxy located on the opposite side of the galactic center from Earth, at a distance of only about 50,000 light-years from the Milky Way's core, making it the closest known galaxy to us, and positioned well within the outer diffuse limits of our galaxy. From the very beginning, researchers suspected that Sagittarius was doomed. Its proximity to the Milky Way meant it was being ripped apart by tidal forces, those same gravitational effects that cause ocean tides on Earth, but operating on a galactic scale, stretching the smaller galaxy along its orbit and stripping away its stars. Numerical simulations showed that when a satellite galaxy gets torn apart by tidal forces from the parent galaxy, it's orbiting. The debris doesn't just scatter randomly, but instead forms coherent streams of stars, both leading and trailing the satellite along its orbit, like a comet's tail stretched in both directions. If this theory was correct, then astronomers should be able to find remnants of Sagittarius strewn along its entire orbital path, forming two diffuse streams that completely encircle the Milky Way. The problem was that these streams would be extremely faint and spread out, so much so that they might be completely indistinguishable, even at short distances from the center of Sagittarius itself, making detection incredibly challenging. But in 2001, researchers from the Institut d'Astrophysique de Canarias, using the 2.5-meter Isaac Newton telescope at Roca de los Muchachos Observatory on La Palma, managed to identify an excess of young stars belonging to a stellar system located 56 kiloparsecs roughly 183,000 light-years, the center of the Milky Way, and these stars had chemical compositions and orbital properties matching what you'd expect from Sagittarius debris. This discovery provided practically incontrovertible direct observational proof, not only that Sagittarius was in an advanced stage of destruction, but more importantly, that galactic cannibalism had played and continues to play a crucial role in the formation and growth of the Milky Way. The Sagittarius stream isn't the only evidence. The galactic halo surrounding the Milky Way's disk is populated with stars that have strange, highly elliptical orbits, many of which are believed to be the leftovers of galaxies our Milky Way devoured billions of years ago. These stars don't participate in the orderly rotation of the galactic disk, but instead follow chaotic paths that bring them plunging through the disk, swinging far out into the halo, and then diving back down again in elongated ellipses that betray their foreign origins. For years, astronomers believed that most of these oddball stars came from a single massive event called the Gaia Sausage Enceladus merger, abbreviated GSE, which was thought to have occurred between 8 and 11 billion years ago, when the Milky Way was still in its infancy. According to this model, a massive dwarf galaxy collided with the young Milky Way in a violent head-on crash that dumped enormous numbers of stars into highly radial orbits, meaning orbits that carry stars close to the galactic center, before flinging them back out again. And this ancient merger was believed to be the last major collision our galaxy experienced. But the Gaia Space Telescope, which has precisely measured the positions and motions of over 1.5 billion stars, has completely rewritten this story by discovering something astronomers call wrinkles, ripples in the distribution and motion of stars that propagate through the galaxy like waves, spreading across the surface of a pond. These wrinkles form each time stars from a merger swing back and forth through the center of the Milky Way. And crucially, the number and sharpness of the wrinkles tells you how long ago the merger happened. If a collision occurred 8 billion years ago, the stars would have passed through the galactic center so many times that the wrinkles would be stacked right next to each other, blurring together into an indistinguishable mess. But if the collision was more recent, the wrinkles would still be distinct and clearly visible as separate features. When Thomas Donlan and his team at Rensselaer Polytechnic Institute compared Gaia's observations to computer simulations of galactic collisions, they made a stunning discovery. The wrinkles visible in the real data are far too sharp and well-defined to have been created 8 to 11 billion years ago. By matching the simulated wrinkles to the observed patterns, the team determined that the Milky Way's last major collision actually happened around 2.7 billion years ago, at least 5 billion years later than previously thought. And they named this event the Virgo radial merger. This finding throws a massive wrench into our understanding of the Milky Way's history, because it means the galaxy was already fairly mature, not a young infant, when it experienced its most recent major cannibalism event. And many popular models of how the Milky Way grew would consider a recent head-on collision with a dwarf galaxy of this mass to be extremely rare. The Virgo radial merger likely brought with it a family of even smaller dwarf galaxies and star clusters that all got devoured by the Milky Way at around the same time, adding complexity to an already chaotic picture. The discovery also calls into question whether all the stars previously attributed to the ancient GSE merger actually came from that event. Some might instead be remnants of the more recent Virgo collision, and future Gaia data releases will hopefully clarify which stars belong to which merger. The fact that the Milky Way's history keeps getting rewritten with each new dataset shows just how much we still don't understand about our own cosmic backyard, and it highlights how powerful precision measurements from missions like Gaia can be in revealing secrets hidden in plain sight. The Milky Way isn't unique in this cannibalistic behavior. Our nearest large galactic neighbor, the Andromeda galaxy, located about 2.5 million light-years away, shows extensive evidence of similar merger activity. In 2001, astronomers conducting a deep panoramic imaging survey of Andromeda's halo with the Isaac Newton telescope discovered an extended stream of stars protruding from the galaxy, clear evidence that Andromeda had recently torn apart one of its satellite galaxies. The distribution of globular clusters around both the Milky Way and Andromeda matches what computer simulations predict for galaxies that have grown through repeated acts of cannibalism, suggesting that this violent process is not some rare aberration, but the standard way that large spiral galaxies build themselves up over cosmic time. The cannibalism can even cascade to smaller scales. In 2021, astronomers discovered that the Large Magellanic Cloud, itself a satellite galaxy orbiting the Milky Way, had previously cannibalized an even smaller galaxy that was once its own satellite, creating a cosmic hierarchy of galactic predation where everyone is eating everyone else. These mergers and collisions aren't gentle affairs when two galaxies interact gravitationally. Stars can be flung into entirely new orbits. Gas clouds can collide and compress to trigger massive bursts of star formation, and the structure of both galaxies can be fundamentally reshaped. The Milky Way's central bar, that elongated structure of stars cutting through the galactic core, might itself have been triggered or enhanced by ancient merger events that pumped energy into the disk and caused stars to reorganize into this configuration. The supermassive black hole at the galaxy's center, currently weighing in at about 4 million solar masses, may have grown substantially by devouring gas funneled inward during violent collisions. As astronomers map more stellar streams and study the chemical compositions of halo stars, they're piecing together a detailed timeline of the Milky Way's cannibalistic past, which galaxies were consumed when, how massive they were, and what impact each merger had on the galaxy's evolution. Some estimates suggest that the Milky Way has absorbed dozens of smaller dwarf galaxies over its 13.6 billion year lifetime, with each victim contributing stars, gas, heavy elements, and dark matter to the growing galactic behemoth. The process continues today. Sagittarius is still being actively shredded. The Magellanic Clouds are on trajectories that will eventually bring them into direct collision with the Milky Way's disk, and numerous ultra-faint dwarf galaxies lurking in the outer halo are gradually losing their stars to tidal stripping. But the Milky Way's cannibalistic spree won't last forever. In roughly 4 billion years, the galaxy will experience its most dramatic collision yet, when Andromeda, currently racing toward us at about 75 miles per second, finally crashes into the Milky Way in a titanic merger that will fundamentally reshape both galaxies. Simulations of this future collision show that the two spiral galaxies will make multiple passes through each other, with each encounter becoming more violent as their orbits decay and they spiral closer together, eventually merging into a single giant elliptical galaxy that astronomers have already nicknamed Milkomeda. During this merger, which will take place over the course of several billion years, stars from both galaxies will be flung into new orbits. The galactic disks will be disrupted and destroyed. Enormous bursts of star formation will ignite as gas clouds collide, and the two central supermassive black holes, one from each galaxy, will eventually sink to the center of the merged system and coalesce into an even more massive black hole. The solar system will likely survive this collision intact, because stars are so far apart that direct collisions are incredibly rare. But our position within the newly formed elliptical galaxy will be completely different, and the night sky will look utterly alien, with a dramatically different arrangement of stars and no recognizable constellations. This upcoming merger with Andromeda is just the latest chapter in a story that's been playing out since the first generation of galaxies formed in the early universe. Structures growing through collisions and cannibalism, smaller systems being absorbed into larger ones, and the relentless march toward ever more massive galaxies, driven by the inexorable pull of gravity. The Milky Way's scattered stellar streams, its strangely orbiting halo stars, and the ghostly remnants of Sagittarius all serve as permanent reminders that our galaxy is built from the corpses of countless smaller galaxies, each one contributing its own unique population of stars to the cosmic city we call home. Beyond the visible spiral arms, glowing nebulae, and countless stars that make up the Milky Way's luminous disk, lies something far stranger and more massive, an enormous, invisible halo of dark matter that extends hundreds of thousands of light years into space, completely dwarfing everything we can actually see and outweighing all the galaxy's stars. Gas and dust combined by a factor of at least 10 to 1. This dark matter halo is the true foundation of our galaxy, the invisible scaffolding that holds everything together through gravity alone. Yet it refuses to interact with light in any detectable way, making it one of the greatest mysteries in modern astrophysics. The evidence for this massive invisible structure comes primarily from rotation curves, measurements of how fast stars and gas clouds orbit the galactic center at different distances. According to basic physics, if you have a massive object like the Sun with all its mass concentrated at the center, objects farther away should orbit more slowly, which is exactly what we see in the solar system, where Mercury whips around at nearly 35 miles per second, while distant Neptune crawls along at a leisurely 3.5 miles per second. But when astronomers measured the orbital speeds of stars and gas clouds at different distances from the Milky Way's center, they found something bizarre. Instead of slowing down as you move farther out, the rotation speed stays roughly constant, even at the very edges of the visible disk and beyond. This flat rotation curve can only be explained if there's a huge amount of invisible mass spread throughout a roughly spherical halo extending far beyond the visible galaxy, providing the extra gravitational pull needed to keep those outer stars moving so fast. Without this dark matter halo, the outer regions of the galaxy would be spinning so fast that stars would simply fly off into intergalactic space like water droplets flung from a spinning wheel, and the Milky Way would tear itself apart. Current estimates suggest the luminous matter in the Milky Way, all the stars, planets, gas, and dust we can actually see, adds up to about 90 billion times the mass of the Sun. But the dark matter halo weighs in at somewhere between 600 billion and 3 trillion solar masses, meaning dark matter comprises roughly 95% of the galaxy's total mass. The precise structure and shape of this halo remain frustratingly uncertain despite decades of research, partly because dark matter only reveals itself through gravity, and partly because we're stuck inside the very structure we're trying to map. For years, astronomers assumed the dark matter halo was roughly spherical, a simple assumption that made calculations easier. But recent observations of the stellar halo, that cloud of ancient stars orbiting in the outer reaches of the galaxy, suggest the dark matter distribution is far more complex. When researchers analyze the positions and motions of stars from the Gaia Sausage Enceladus merger, that ancient collision between the Milky Way and a dwarf galaxy that dumped millions of stars into elongated orbits, they discovered that these stars don't arrange themselves in a simple spherical pattern, but instead form a triaxial structure, basically an elongated football shape that's tilted at an angle relative to the galactic disk. This tilt is around 25 to 35 degrees at various distances from the galactic center, and the structure itself appears to be Zeppelin-shaped rather than spherical. If this stellar halo configuration has been stable for billions of years, which the observations suggest it has, then the underlying dark matter halo must have a similar triaxial shape and tilt to provide the gravitational framework that supports the structure. Sophisticated computer models that simulate the orbits of millions of stars in different gravitational potentials show that only a dark matter halo with an axis ratio of about 0.87, meaning it's elongated rather than spherical, inclined at roughly 43 degrees to the galactic plane, can reproduce the observed distribution and motions of the Gaia sausage Enceladus stars. SARS, a perfectly spherical dark matter halo, simply cannot support the triaxial tilted stellar structure that astronomers observe, definitively ruling out the simplest models. This discovery has profound implications, because it means the Milky Way's dark matter isn't smoothly distributed, but instead has preferred directions and orientations influenced by the galaxy's formation history, ancient mergers, and ongoing interactions with satellite galaxies. The dark matter halo isn't just a static, unchanging backdrop either. Cosmological simulations predict it should be clumpy and filled with smaller concentrations called subhalos, dense knots of dark matter ranging in mass from millions to billions of solar masses that formed independently in the early universe and later got swallowed by the growing Milky Way halo. These subhalos act as invisible anchors that can gravitationally perturb passing stars and gas clouds, and they're predicted to number in the hundreds or thousands throughout the Milky Way's halo, based on the lambda-cold dark matter model of cosmology. Until recently, evidence for these subhalos was entirely indirect. Astronomers noticed unexplained gaps and distortions in stellar streams, those ribbons of stars torn from disrupted globular clusters, and hypothesized that invisible dark matter subhalos must have gravitationally tugged on the streams as they passed by. But in 2025, researchers may have detected the first direct signature of a dark matter subhalo lurking just a few thousand light-years from Earth, identified through its gravitational influence on nearby stellar motions. If confirmed, this detection would validate a key prediction of the cold dark matter model and demonstrate that the halo is indeed lumpy and structured rather than smooth. Perhaps the most tantalizing recent development comes from gamma-ray observations that might represent the first direct detection of dark matter particles after nearly a century of searching. NASA's Fermi Gamma Ray Space Telescope, which has been scanning the sky for high-energy radiation since 2008, has detected a mysterious halo-like glow of gamma rays surrounding the Milky Way that peaks sharply at energies around 20 giga-electron-volts. That's 20 billion electron volts per photon, an absolutely staggering amount of energy. The shape and intensity of this gamma-ray emission closely matches theoretical predictions for what you'd expect if dark matter particles, called weakly interacting massive particles, or WIMPs, were colliding with each other and annihilating in the galactic halo. According to this model, when two WIMPs collide, they destroy each other completely, converting their mass into pure energy in the form of gamma rays, with a very specific energy spectrum, determined by the mass of the particles. The observed signal peaks at exactly the energy you'd expect from WIMPs, with masses about 500 times heavier than a proton, and the spatial distribution of the gamma rays matches the expected dark matter density profile remarkably well. The researcher who discovered this signal, Tomonori Totani from the University of Tokyo, spent years carefully analyzing 15 years of Fermi data, painstakingly subtracting all known sources of gamma rays, including interactions between cosmic rays and interstellar gas emissions from the Fermi bubbles, those giant structures of hot plasma erupting from the galactic center, and countless other astrophysical processes that produce high-energy radiation. After removing all these contributions, a residual component remained that shouldn't be there according to conventional astrophysics. And this excess emission has exactly the properties predicted for dark matter annihilation. But before we pop the champagne and declare dark matter detected, independent experts are urging extreme caution, because proving this signal actually comes from dark matter rather than some unknown astrophysical process is extraordinarily difficult. The galactic halo is filled with complex, poorly understood phenomena: diffuse cosmic rays, magnetic fields, faint stellar populations, and various forms of interstellar matter, any of which could potentially produce gamma-ray emissions that mimic a dark matter signal. A similar excess of gamma rays was previously detected, coming from the galactic center itself, and that signal has been debated for over a decade, with no definitive conclusion about whether it's dark matter or something more mundane, like emissions from a large population of millisecond pulsars. The new halo signal will require years of additional observations, cross-checks with other telescopes, and detailed modeling to verify. And even then, the case might not be conclusive unless someone builds a detector sensitive enough to directly catch dark matter particles interacting with normal matter in a laboratory. What makes the dark matter halo especially mind-bending is its sheer scale. While the visible disk of the Milky Way extends about 50 to 60,000 light-years from the center, the dark matter halo is believed to stretch at least 200,000 to 300,000 light-years, and possibly much farther, perhaps up to 600,000 or even a million light-years, before it finally fades away and merges into the intergalactic medium. This means the Milky Way's gravitational influence extends vastly farther into space than you'd ever guess by looking at images of the galaxy and satellite galaxies, like the Magellanic Clouds, orbiting 150 to 200,000 light-years away, are still well within the Milky Way's dark matter halo and subject to its gravitational pull. The density of dark matter drops off with distance from the galactic center, falling from around 0.0088 solar masses per cubic parsec at the sun's location, which sounds like a lot, until you realize a parsec cubed is an absolutely enormous volume, meaning dark matter is incredibly diffuse to far lower densities in the outer halo, where individual dark matter particles might be separated by thousands or millions of miles. The exact radial profile of the dark matter density remains controversial, with some evidence suggesting a relatively smooth fall-off, and other studies finding hints of a broken profile, where the density drops much more steeply, beyond about 80,000 light-years. These uncertainties matter enormously for calculating the total mass of the Milky Way and for understanding how our galaxy will evolve in the future, especially as it interacts with Andromeda and other members of the local group. The dark matter halo also plays a crucial role in shaping the galaxy's magnetic field, influencing the paths of cosmic rays and potentially affecting the rate of star formation. By controlling how gas falls into the disk from the surrounding intergalactic medium, all these invisible processes happening in the dark matter halo profoundly impact the visible galaxy we observe, yet we can only infer their existence through subtle gravitational effects and indirect observational signatures, making the study of dark matter one of the most challenging and frustrating endeavors in all of astronomy. We know it's there, we know roughly how much of it there is, but we still have almost no idea what it actually is, what it's made of, or why it refuses to interact with light and normal matter in any way, except through gravity. When you look up at the night sky and see that faint band of light stretching across the darkness, it's easy to feel like the Milky Way represents something vast and infinite. But zoom out to a cosmic perspective, and you quickly realize our home galaxy is actually middle of the pack, dwarfed by galactic titans so enormous they make the Milky Way look like a cosmic dwarf by comparison. The largest known galaxy in the observable universe is IC 1101, a supergiant elliptical galaxy located roughly 1 billion light-years away in the constellation Virgo. And this behemoth stretches an absolutely mind-boggling 4 million light-years from edge to edge. That's roughly 40 to 50 times the diameter of the Milky Way's visible disk. To put that scale in perspective, if you placed IC 1101 where the Milky Way sits, it would extend past Andromeda, past the Triangulum Galaxy, and would encompass virtually the entire local group of galaxies, swallowing dozens of separate galaxies within its boundaries. This monster galaxy contains an estimated 100 trillion stars, roughly 1,000 times more stars than the Milky Way, and most of those stars are ancient red and yellow giants, orbiting in a vast, diffuse swarm that lacks the elegant spiral structure we see in our own galaxy. I-1101 is classified as a supergiant elliptical galaxy, a type of galaxy that forms when multiple large galaxies merge together over billions of years. Their spiral structures destroyed by tidal forces during the collisions, leaving behind a featureless ball of stars with no organized rotation or distinct arms. The second largest galaxy currently known is Hercules A, another supergiant elliptical with an estimated diameter of 1.5 million light-years, making it roughly 15 times wider than the Milky Way. Hercules A sits at the center of a massive galaxy cluster and appears to have grown to its current size by cannibalizing every galaxy unfortunate enough to wander into its gravitational reach. And the galaxy is also notable for hosting a supermassive black hole at its core that shoots out twin jets of matter and energy, stretching hundreds of thousands of light-years into space. The third largest galaxy, designated A2261 BCG, the initials stand for Brightest Cluster Galaxy, because it's the most luminous member of the Abell 2261 galaxy cluster, measures about 1 million light-years across, and contains an estimated 10 trillion stars. What makes a 2261 BCG particularly strange is that despite its enormous mass, astronomers have been unable to locate a supermassive black hole at its center, suggesting that something catastrophic may have happened in the galaxy's past. Perhaps a collision with another galaxy that caused the black holes to merge and then recoil out of the galaxy entirely due to gravitational wave radiation. ESO 30617, another million light-year monster, holds the distinction of being the loneliest large galaxy known. It sits in a vast empty region of space, with no other galaxies nearby, leading astronomers to believe it may have merged with and completely absorbed every single galaxy that once existed in its neighborhood, growing fat on cosmic cannibalism until nothing remained to consume. When you compare these giants to the Milky Way, which measures about 87,400 light-years in diameter, according to recent measurements, our galaxy looks downright modest. Even our nearest large neighbor, the Andromeda galaxy, located 2.5 million light-years away, is roughly twice the size of the Milky Way, at about 152,000 light-years across, making it the 10th largest galaxy known, and significantly more massive than our home. Andromeda contains an estimated 1 trillion stars, compared to the Milky Way's 200 to 400 billion, meaning Andromeda has at least twice as many stars as our entire galaxy. The largest spiral galaxy currently known is UGC 2885, sometimes called Rubin's Galaxy, after astronomer Vera Rubin, which stretches an incredible 438,000 light-years across, roughly 5 times the diameter of the Milky Way. Unlike the giant elliptical galaxies that grew through violent mergers, UGC 2885 appears to have grown slowly and peacefully, gradually accumulating gas and dust from the intergalactic medium and converting it into stars over billions of years without experiencing any major collisions. The Condor Galaxy, a spiral stretching 522,000 light-years, has 2 enormously elongated spiral arms that astronomers believe were stretched out by a glancing collision with another galaxy millions of years ago, creating a structure that looks utterly alien compared to the neat, tightly wound arms of the Milky Way. But the universe doesn't just contain giants. It also harbors countless dwarf galaxies, ranging from tiny irregular systems containing just 100 million stars to somewhat larger structures with several billion stars. The smallest galaxies, called ultra-faint dwarfs, are barely held together by gravity and contain so few stars that they're almost invisible. Yet they're incredibly important for understanding dark matter, because these tiny galaxies appear to have far more dark matter relative to their visible stars than larger galaxies do. The Large and Small Magellanic Clouds, those two satellite galaxies orbiting the Milky Way, measure about 32,500 light-years and 7,000 light-years in diameter respectively, making them small by galactic standards, but still containing billions of stars in active regions of star formation. The entire range of galaxy sizes spans roughly 5 orders of magnitude, from dwarf irregulars, just a few thousand light-years across, to supergiant ellipticals, measuring millions of light-years, and the Milky Way sits comfortably in the middle of this range, large enough to host hundreds of billions of stars, but nowhere near the cosmic titans that dominate the largest galaxy clusters. Galaxy mass tells a similar story. A typical dwarf irregular galaxy might weigh just 100 million times the mass of the Sun, while a giant spiral like the Milky Way clocks in at roughly 1 trillion solar masses. When you include all the dark matter and supergiant ellipticals, like IC 1101 can reach 100 trillion solar masses or more. The observable universe contains an estimated 200 billion to 2 trillion galaxies, depending on which survey you trust, meaning the Milky Way is just one among literally trillions of galactic systems scattered throughout space, each one a vast city of stars with its own unique history, structure, and destiny. Most of these galaxies are small, faint dwarfs that you'd never notice unless you had a powerful telescope, but a significant fraction are large spirals and ellipticals comparable to or larger than the Milky Way, and a small percentage are the supergiant monsters that dominate their cosmic neighborhoods. The question that haunts astronomers is whether there's something special about being medium-sized. The Milky Way's mass, structure, and environment appear to be conducive to the formation of planetary systems and potentially life. But would the same be true in a galaxy 10 times larger or 10 times smaller? A supergiant elliptical, like IC 1101, is filled with old, dying stars and has relatively little gas left to form new stars or planets, making it a poor candidate for hosting civilizations, while ultra-faint dwarfs are so small and metal poor that they probably lack the heavy elements needed to build rocky planets. The Milky Way, with its ongoing star formation, its relative quietness compared to active galactic nuclei, and its rich abundance of heavy elements forged in previous generations of stars, might represent a galactic sweet spot, large enough to be interesting, small enough to be stable. Yet this conclusion comes with a massive caveat. We're fundamentally limited by perspective, because the only example of intelligent life we know of exists in the Milky Way, so we have no idea whether life requires a galaxy like ours, or whether civilizations might thrive in vastly different environments that we'd consider hostile. The Milky Way's position in the cosmic hierarchy also raises questions about our future. When Andromeda and the Milky Way collide in about 4 billion years, the merged system will become significantly larger, probably resembling a giant elliptical galaxy, with a combined mass of around 2 trillion solar masses and a diameter potentially exceeding 200,000 light-years. This new galaxy, nicknamed Milkomeda by astronomers, will rank among the larger galaxies in the universe, though still far short of the supergiant class, and the collision will fundamentally reshape the structure, star formation history, and galactic environment in ways that could dramatically affect any civilizations that still exist at that time. Looking beyond the local group to the broader cosmic web, the Milky Way sits within the Virgo supercluster, an enormous structure containing thousands of galaxies and spanning roughly 100 million light-years. But even that supercluster is just one of countless such structures scattered throughout the observable universe. The observable universe itself extends roughly 93 billion light-years in all directions from Earth. That's the maximum distance light could have traveled since the Big Bang 13.8 billion years ago, accounting for cosmic expansion, making the universe incomparably vaster than even the largest galaxy. Within that colossal volume, the Milky Way is simultaneously significant and utterly insignificant. Significant because it's our home and the only place we know harbors life, but insignificant because it's just one average-sized galaxy among trillions, sitting in a fairly typical region of space with no special claim to cosmic importance. The humbling realization that flows from these comparisons is that for all the Milky Way's apparent grandeur when viewed from within, it's really just a modest spiral galaxy, inhabiting a quiet corner of an unimaginably vast universe. And everything we've ever known, every human who's ever lived, every civilization that's ever risen and fallen has happened within this one unremarkable galaxy that represents less than a trillionth of all the galaxies that exist, raising the profound and unsettling question of whether our existence, our struggles, our achievements mean anything at all on cosmic scales, or whether we're just temporary patterns of complexity in one tiny pocket of an indifferent universe that would barely notice if our entire galaxy vanished tomorrow.